halides. Then there is also, we can also form alkenes from alcohol. Okay, the hydration of alcohols. Now you studied this in O level, okay, but you didn't do the mechanism. So today we are going to do the mechanism and see how the mechanism is. So when these alcohols are heated with conc sulfuric acid, or now you heat with conc sulfuric acid or phosphoric acid, and this one, the reaction occurs at room temperature. You don't even need to heat. Okay, now the alcohol must either be in liquid form or vapor phase, but usually the vapor phase is preferred. But for this one, it can react when it is in liquid form or in vapor phase. So this, for phosphoric acid, it doesn't mind. You form an alkene. But for sulfuric acid, my dear, here you must be specific. Okay? And we are going to see, if you don't specify the temperature, that you'll be able to form totally different things, different compounds, as I'm going to show you. Okay, so the conditions are heat. You must heat, and not just heat, but at a given range of temperatures. And in this case, it is 170 to 180 depending on the alcohol that you are using. Okay, that is if you are using conc sulfuric acid. Conc sulfuric acid. And number two, the acid that you are using must be concentrated. The acid must be concentrated. In that, here if you use a dilute acid, then you cannot get any results. Okay? Yes. So that is your equation. The alcohol, which is ethanol in this case, plus conc sulfuric acid in presence of, so you heat it at this temperature. Now when you are writing a paper, you don't put the range also. You choose one temperature in this range. Okay, either you choose 180 or you choose 170, okay, or you choose one, but you write one specific temperature, not a range. Okay. Sorry. Then you're going to form your alkene. So this is a dehydration reaction. Why? Because you are removing water molecule. You are drying. You know, one of the properties of sulfuric acid. Sorry. One of the properties of sulfuric acid, conc sulfuric acid, is it dehydrates. Okay. So this property is manifested here in that when you react it with ethanol or any alcohol, then you form an alkene. So the mechanism, it is simple. Your conc sulfuric acid, okay? Your conc sulfuric acid, it will it is a weak acid. Why? Conc has concentrated sulfuric acid. It is a weak acid. Why? Because it undergoes partial dissociation or partial ionization to give you hydrogen ions, okay, and hydrogen sulfate ions. Okay, now if you want, this is hydrogen sulfate ions, or if you want, you can write it as this. It is all the same thing. So this is oxygen, this is so it is all the same thing. Okay, now this is the first step. The first step is dissociation, okay, of the acid. Then the next step is protonation of the alcohol. Why are you protonating the alcohol? Because the alcohol already has a leaving group. When we write our alcohol like this, CH3, CH2, then OH, OH. Now, this OH is already a good leaving group, okay? But to increase on the reaction, this acid is a catalyst. So to increase the rate of reaction, then you further protonate this alcohol so that you increase, okay, the livingness in quotes of this OH, so that you form a protonated alcohol. So how are we going to do it? This is oxygen. It has a lone pair of electrons. In fact, two lone pairs of electrons. But for us here, we are interested in one. And this is how we represent a lone pair. Okay? Now, this hydrogen is a proton. Okay? It has lost its one electron to this oxygen here. So in other words, this is an electrophile. Okay? And this one, it is a nucleophile. So what will happen is this O, the O is going to donate its lone pairs of electrons, okay, to this hydrogen. Are you seeing that? Okay, so that what do you form? You will form a protonated alcohol, an alcohol which is protonated, and that protonated alcohol has a very good leaving group. So you form CH3, CH2, okay, with this bond, then O with the O2. Now you see, this oxygen has lost its electrons. Are you seeing that? And on top of that, it has three bonds. One, two, three. These two hydrogens. So to balance the equation, then we put a plus on this oxygen. That if you don't put a plus here, then we cross, because we don't know. That is not chemistry. Okay? So this is what we call a protonated alcohol. And so this OH2 is a good leaving group that it will easily dissociate to form a primary carbocation and forms water as a neutral molecule. So this is CH, CH3, okay, CH. Now, because this carbon has lost the O, okay, and because this carbon, the bonds are not balancing, it has 1, 2, 3, and it has lost the O, then you put a plus here. So this is a primary carbocation, okay, plus the water molecule. Is that okay? Good. Now, this is where the science is, okay. Now to balance the equation, okay, then this hydrogen sulfate ions, these ones, being highly nucleophilic. Because of this, the oxygen has two lone pairs of electrons, and on top of that, it has received even electrons. So this one is highly nucleophilic. So what happens? Let me first get some pen to avoid issues of writing. Let me remove this, okay, to avoid issues of writing. So if I put a 2 here and I spread this bond, okay, it is still the same thing. So these hydrogen sulfate ions, or S3, whichever way you write it, we shall give you marks. Whether I write this, it is still the same thing. But I have to write all of them so that you don't find this in the books and you get confused. Or you don't find this in the books and you get confused. So if you find this, it is still hydrogen sulfide ions. So this one, it will take away. It will take away this hydrogen. Okay? Okay? And then this bond of carbon hydrogen, the electrons in this bond are taken up by this carbon. But when they are taken up by this carbon, then they will be used to form a pi bond. Okay? So to summarize that, we represent that as this. The arrows must touch, please. The arrows must touch. So as a result, what do you form? You form CH2. Can you write with me? CH2, double bond, and another CH2. As simple as that. Ah, as simple as that. Mm. Now that is science. Can you try out this? Try out this. You have this. Uh-huh. Then you have the OH here. And then conc sulfuric acid. Okay? Conc, conc sulfuric acid. You should be writing. Yes, I might not mark, but you try out and then now you come and write the mechanism so that you see. This is for your own benefit, okay? This is 180 degrees, 180 degrees Celsius. Can you try it out? Please hurry up. Hurry up, please. Hurry up, hurry up, hurry up. Let me give you. It is 58. If it clocks 3, I shall do the mechanism. Please try out. Use this knowledge. Okay? Use this knowledge. This knowledge, it is the same thing. Okay? To do the mechanism. It is the same thing. Nothing is different. So this is cyclohexane. So if you write cyclohexane with conc sulfuric acid at 180, what do you form? You can drop your answers in the chat box. But the mechanism, please do it. Do it. Try to do something. Try to do something. Don't be rebellious, okay? I'm watching you. You. Please do something. Do something. Do something. Hurry up. Hurry up. Hurry up. Hurry up. Actually, it is like this. All of you, when you do the mechanism that you are going to write after the lesson, take a pic of it and send it via WhatsApp. Yes. Take a pic of it and send it via WhatsApp. Eh. So now let me find when you have not sent anything. We shall fight. We shall fight. Murunji, have you finished? Meron? Dennis, Jordan, Herbert? Who else is present? Okay, so let's do the mechanism. Let's do the mechanism together so that you can see, you can compare with what you've done. So it is the same concept. The acid dissociates, okay, to give you hydrogen ions and hydrogen sulfide ions. This is a 3. Don't be confused. So hydrogen sulfide ions, sulfate ions. Now, the next step is protonation, okay, where you're going to protonate the the OH, you're going to protonate. Now you have two lone pairs of electrons, but usually represent 1. So you can circle it, okay? You protonate it, so you have this plus here, then you donate this lone pair of electrons to this hydrogen. That's brilliant. And then you form a protonated alcohol, okay, which is OH2. Now, because this oxygen has lost its electrons, then we put a plus on the oxygen. That step, I hope you are correct. Now, this one being a good leaving group, it will take away these electrons to neutralize the charge on this oxygen. Okay? And so what do you form? Then you form your cyclohexane, okay, which is a secondary carbocation. And so we put a plus here. The plus is on this carbon, okay, but because we cannot spread to show the carbon, then we put a plus here. So did you put your plus here, please? Did you? I don't know what you did. Now after this, then obviously we have now this one. It is the same as writing this, the hydrogen here and the hydrogen here. Okay, so this is the same thing. Now the hydrogen sulfate ions, okay, and this is a 3. This is a 3. I was almost erasing everything, and that is malice. So this is a 3, and then there is H here. Now there is you put a minus here. Now this one, being a nucleophile, it will donate its electrons to this hydrogen and take away this hydrogen, and then the electrons here, they will be used to form a double bond, and that's how you represent it. Okay, and so the result will be so astonishing that you form what? A cyclo. Oh, this is like this. This is like this. Now when you are writing this with a pen, all these sides must be equal. Okay, I repeat, when you are writing this with a pen, all the sides must be equal. Not, don't be mad. So with a double bond here, and this one is cyclohexene. So it is as simple as this. So did you get this? Yes, if you got in that, then you are a good boy, you are a good girl. Now, so if somebody has something to say? Okay, now there is a concept that I want to introduce. Let me see if it is down. The concept is here. The carbon arrangement. Let me first erase this. Can we please mute? The concept of carbon arrangement, e.g. in dehydration of 2-methyl 3-pentyl. 2-methyl 3-pentyl. Oh, sorry for that. This concept is so good. So good. Okay? That please be as attentive as possible. So you have this CH3, CH, and then you have a methyl group here, okay, and then CH, this is CH2, and you have the OH here, so the 2 is not there, and then you have CH, okay, CH3. Let me simplify and write this. It is going to bring out the mechanism. Let me rub this cartoon. So now, for such an equation, if you react it with concentrated, okay, sulfuric acid, okay, at 180 degrees Celsius. Now, there are two products that you can form, where one, you can form this CH3, CH, and then the methyl group is here, and then you form use single bond, and then this. So you can form this with a double bond here. So there is a possibility of forming that. Or there is a possibility of forming this CH3, CH2, CH. No, there is no H. There is no H. Let me erase it. There is no H. There is no H. Double bond with a methyl group. Then CH. Then CH3. So there is a possibility of forming all these compounds. Okay? Yes, they are going to be formed, but in different amounts, where one is a major compound and another one is a minor compound. And this one, it will be a minor compound, like you form something like 20%. I'm estimating, I'm not saying that that's the percentage. Then this one, you form 80, and this will be the major compound. Now, how can you explain that? By the way, this very question can be asked in explanation questions. They will say, explain why reaction of this one is 2,3,2-methyl butane 2 or reacted with this at 180 degrees Celsius, you form this instead of this. Explain. Okay? So the explanation is simple. This one is going to dissociate automatically. Let me dissociate it. Okay? You can dissociate it with me. You can be writing your mechanism. Conc sulfuric acid. It is a weak acid. I'm saying conc sulfuric acid. So it will partially dissociate to give you the hydrogen ions, okay, plus the hydrogen sulfide ions. So you can write them as this. It is all the same thing. So this is 3, this is H. Now that is first step. Let's first divide our bond. Now that is first step. Now the second step is protonation of our alcohol. So let us protonate our alcohol. So this one, this is a 3. I'm writing this, so don't mind if. So this one is C. This is a methyl group. Okay, this is a methyl group, and then this is the H. This is the C. This is the CH. This is our OH. That's our OH. And finally CH3. So as simple as that. Now this oxygen, we said that it has lone pairs of electrons. Okay, so it will donate the lone pairs of electrons to this proton. Now mind about the direction of your arrows. Now I call it madness if I find somebody drawing such an arrow. This is total madness. Total madness. Why? The arrow shows movement of electrons, and electrons always move from nucleophiles or electron-rich species to electrophiles or electron deficient species. Now if you write such an arrow, really, let me even rub it before you screenshot and beat me the book in quotes. So electrons will always move from electron-rich species, okay, to electron deficient species. And do you see my arrow? It is touching. It has where it is coming from. It has where it is going. So that is what you are supposed to do. So after doing this, then you write your product. And the product is CH3. Then C with your methyl group here. Methyl group here with your hydrogen here. Okay, that's pretty good. And then with the CH, and then the OH Okay, let's first finish this. Okay, sorry. Then the OH, and the OH, it is protonated, so you have OH2, okay, with a plus on the oxygen. Now, because of this one is a good leaving group, so being a good leaving group, it will easily take away the electrons from carbon oxygen bond, and so it is lost as a water molecule. Is that okay? So what you form is CH3, then C, then you have your methyl group here, then you have your hydrogen here. Let me put it here. I'm going to rub it. Then you have your CH, then CH3. Now this is where the science is. Let me first rub this one. Let me rub this one. Now that's where the science is. And the science is simple. These two, there is a plus here. So this is a primary carbocation, and we have three types of carbocations, so carbonium ions. Where, let me write it here, we have the primary. Did I say this is primary? Sorry for that, this is secondary. So we have the primary, where the carbocation is bonded to an alkyl group, okay, the central carbon atom, and the rest are hydrogens. This is a hydrogen, and this one is a hydrogen. Now this is a primary carbocation, or you can say primary carbonium ion. Then for the secondary, okay, the central carbon atom, okay, is bonded to two alkyl groups, okay, that is one, and that is the second one, okay. Then the rest is hydrogen. The third, it is the tertiary carbonium ion, where the central carbon atom, okay, is bonded to three. All the three are alkyl groups. As simple as that. And these alkyl groups have a positive inductive effect in that they push these bonding electrons towards this central carbon atom, and so they will end up stabilizing it. So the more alkyl groups you have, the more stable the carbonium ion. So as a result, the tertiary carbocation is going to be more stable than the secondary carbocation, and the secondary also is going to be more stable than the primary carbocation. Is that okay? Now bring this concept, bring it here. That in this molecule, you have a secondary carbocation. This carbon atom, you see, it is bonded to this alkyl group and this alkyl group. The rest is one hydrogen, which is this. Okay? Now, there is a possibility of forming a tertiary carbonium ion. And a tertiary carbocation is more stable than a secondary carbocation. Okay? So how are we going to form it? Let me get some pen here. It may be red. If I get this hydrogen and I transfer it with its electrons to this carbon atom, okay, and we call this hydride shift, okay, because it is going as a hydride. Now hydrogen also has some unique chemistry, that it can exist as a hydride, that is hydrogen that has received the electrons. It can exist as a proton, that is hydrogen that has lost its one electron, or it can exist as a neutral molecule. So that is hydrogen. Okay? So in this case, the hydrogen has received the one electron, so it has two electrons. So it is a hydride. and so it has a negative charge because it has received. But in this case, the hydrogen has lost its K1 electron. Okay? And so it gains a positive charge. So it is a proton. So you should always take care. Now, in this case, it moves, it goes as a hydride. But in this case, it is a proton. Okay? So this hydrogen is going to go with these two electrons and it shifts to this new position. Okay? And we call that one a hydride shift. You can also write it. And so when you shift, then what will you form? You're going to form a new compound, okay, which is CH3, and then C with a methyl group here, okay. I hope that's brilliant. With a methyl group here with a plus on this, and then CH2, okay, CH2, and then CH3. Now, isn't this one a tertiary carbocation, which is more stable? Yes, it is. Now our compound is stable now that it can proceed to the next step. So when immediately, the moment you form this, then the compound undergoes configurational changes, undergoes rearrangement, okay, to form a tertiary carbocation, which is unstable, sorry, which is more stable than a secondary carbocation. Even if there was a chance of forming a secondary carbocation from a primary carbocation. For instance, if it is this, you have C, and then you have the CH here, okay? You have the CH here, and then you have the CH2, with a plus, okay? With a plus. Mhm. Let me put this hydrogen here, okay? Let me do this, the hydrogen, and let me put the plus here with a plus. Now this is a primary carbocation, this one, but the primary is unstable compared to the secondary, but there is a possibility of forming a secondary carbocation. Oh, sorry for this, sorry for this. Let me erase this, and erase this also, and put this, the hydrogen here. That's good. So this one, there is a 2 here, okay. So this one is a primary carbocation. You can see this is an alkyl group, don't get confused. So a primary is unstable compared to a secondary carbocation. So as a result, this one, it is going to undergo what we call a proton shift, where this hydrogen is going to, sorry, a hydride shift, where this hydrogen is going to shift as a hydride with its 2 electrons from this carbon to this new carbon. So as a result, you form a secondary carbocation, okay? A secondary carbocation. Oh my God. R, then C, then CH3, okay, CH3. In fact, this is a tertiary carbocation, and then this is CH3. So this is a tertiary carbocation, and now this is stable, so it can proceed to the next step. Is that okay? Feel free to contact. Now the next step is obviously very easy. You can now show the next step is very easy. Just remove that. Let's remove the 2. Let's remove the 2, and we put this, and we put this here. We bring our hydrogen sulfate. Then we take away this hydrogen, and then we bring this here, and we form our final compound. So that is the chemistry. And okay, let me write the final compound for the benefit of the viewers. This is CH3, CH3, double bond, CH3, sorry, CH, and finally CH3. So it is as simple as this. Is that okay? Let me go and check the chat box. Let me keep it.